Many of us envision a future, right, in which we as a species gain the ability to live or at least have bases in other parts of our solar system. Now, the closest example of this right now is the moon. And surely you have heard many people, myself included, also talk about Mars. Now, we may still be somewhat far away from having the technology to do this full on, but things like the International Space Station have helped teach us what it is like to live in space, even if it does not fully replicate what it might be like to have a base on a planet or another moon. Now, what if? Listen. Hear me out. What if we wanted to someday establish a base further out into our solar system? I think that this is a pretty reasonable thing to expect. In such an event, what might some good options be? Now, there may not be one right answer here. In fact, I'm certain that there is not. But the one that comes to my mind first is Jupiter's moon Callisto. So for today, let's learn more about the moon, its formation and characteristics, and some other fun facts about it. And then we're also going to learn about what it takes to set up a moon base to begin with, and we can kind of put these things together to see why Callisto might be a potential candidate. Now, I will admit, okay, I'm coming out, outing myself. This probably could have been 2 separate videos, but as I was putting it together, I thought it might be fun to turn it into one. Callisto was discovered on January 7th, 1610, using one of the world's first telescopes. Now, this discovery is credited to 2 astronomers, Simon Marius and Galileo Galilei, both of whom found the moon independently. It was discovered alongside Jupiter's other 3 large moons, being Io, Europa, and Ganymede. Today, these are referred to as the Galilean moons, named after Galileo, but Callisto's name itself was actually proposed by Simon Marius. Now, it and the other large moons are easily visible with a pair of good binoculars. And we have since gone on to discover 97 other smaller moons, bringing the total for Jupiter up to a whopping 101. It is worth noting that this is the number of officially recognized moons, and that Jupiter has thousands of smaller, uncatalogued objects that are orbiting it. With that being said, let us continue by looking at how it formed, what it's composed of, and where it ended up in relation to Jupiter and its counterpart large moons. Now, Callisto likely formed alongside the other 4 Galilean moons roughly 4.5 billion years ago, and Callisto formed through a process called slow accretion within what is known as the Jovian subnebula. The amount of time that it took Callisto to form is not concretely known, but we suspect it took, and this is quite a range here, now that I look at it again, between 0.1 million and 10 million years. This also makes it the slowest of the Galilean moons to form. Not only that, but it formed the farthest away from Jupiter of the 4 large moons, and that's important. We'll get back to it later. Today, it is around 1.17 million miles away from Jupiter, its host planet. For comparison, this is roughly 6 times the distance that our moon is from us here on Earth. This distance means that it does not experience significant tidal heating, nor did it during its formation. Combine this lack of heating and the long formation times, and what you get is a partially differentiated core. meaning that during formation, the moon did not melt all the way through, and so rather than the materials and elements inside of it fully melding together, they formed into layers. So before moving on to that, right, let's return to a couple of reasons why Callisto would make for a good future moon base. And the main one is that distance that I mentioned earlier. See, Callisto is far enough away from Jupiter that it sits outside of the planet's radiation belt. So it receives significantly, and I mean significantly less radiation than the other large moons. This means it would be much safer for humans to inhabit, as safe as a moon base can be. And Jupiter, and by extension Callisto, is also in a strategic position when it comes to exploration, right? Because it would make the asteroid belt and the outer planets a lot more easily accessible to us than they are today. Depending on what presence we may be able to achieve, Callisto would serve for a great hub of sorts, a midway point, if you will, in exploring further out. Along with this, Callisto offers access to an important resource through its abundance of water ice. So there is something in space travel and exploration known as in situ resource utilization. I definitely think there could be a better name for that, but I'm not in charge, and it is what it is. So what is this? Well, it is the practice of collecting, processing, and using materials found on the location that you are exploring, rather than trying to carry it all with you. So to help with creating and growing food, oxygen, construction materials, and even fuel for future trips, water is important in all of that, right? In short, there's a saying in space travel: if you try to bring everything with you, you have already lost. Like I just mentioned, water is used in so many things and is outright just vital to life. But it is also heavy and difficult to bring to space. So for a base to truly succeed on far-off places like the Moon, Mars, or definitely Callisto, we need to bring enough resources to bootstrap the base at the get-go, but then transition into making use of on-site resources. But by now you might be wondering, man on the internet, what else is Callisto composed of? Right, we can't make a base on a ball of ice now, can we? And you would probably be right about that. I think it would be pretty hard. So joining that water ice, Callisto also contains rocky material at roughly equal parts, coming in at around 49 to 50% ice. Toss in some additional ammonia, and you have yourselves one Callisto. Of Jupiter's major moons, Callisto has the lowest density and surface gravity. So launching off of it would be easy. So like earlier I mentioned that it could be a waypoint of sorts. Well, the lower gravity you have, the easier it is to launch off of that. This is an advantage we'll get from the moon as well. For Callisto's rocky component, while its exact nature is unknown, scientists believe that it is close in composition to an L or LL type ordinary chondrite, which are commonly viewed as representatives of primitive nebula, matter, or even building blocks, if you will. So it does make sense that these early rocks would wind up within the core of Callisto, on the surface of Callisto, and even within the other Galilean moons. So if we were to take a cross-section of Callisto based off current data, this is what we might see. Its cold, rigid outer shell of crust, or crust if you will. So if we were to take a cross-section, right, of Callisto based off of current data, this is what we might see. Its cold, rigid outer shell, or crust if you will, sits somewhere between 80 and 150 kilometers thick. and it is called the lithosphere. Beneath it, we believe might sit a subsurface ocean at depths of 100 to 250 kilometers beneath the lithosphere. While Callisto does not have a strong magnetic field like its counterpart Ganymede, it does have a weak induced magnetic field which forms as it passes through parts of Jupiter's rotating magnetic field. It is the theorized saltwater ocean that induces these electric currents and lead to that weak magnetic field. So that is another hint towards that liquid saltwater ocean being there. And as Callisto is one of Jupiter's icy moons, while we're here, let's talk a bit about that potential subsurface ocean. The data for this comes to us from the Galileo spacecraft's magnometer. Magnometer. I'm pretty sure I butchered that one every time. Anyway, it suggests that the subsurface ocean is saltwater, with salinity that is potentially comparable to seawater here on Earth. It also suggests the presence of a small amount of ammonia, up to 5% of the total water by weight. What this achieves is the lowering of the freezing point of said water, which would allow it to continue existing as a liquid and not just turn into a solid. That being said, a heat source is still required to help keep the water from freezing, and unlike Europa, which is experiencing intense tidal heating, Callisto has no such thing. Instead, its heat is generated by internal radioactive decay that is insulated by the outer shell. While it is possible for Callisto to harbor life, scientists consider its chances to be lower than its counterpart moon Europa, because of its lower level of heating, along with its rocky core potentially having less contact with that subsurface ocean. This would result, in less heat and nutrients reaching the water. Despite that, it is still on the docket to be explored by ESA's Jupiter Icy Moons Explorer, known as JUICE, and even the NASA Europa Clipper mission. But enough about the moon itself. Now we talk moon bases. So, when talking about moon bases, we cannot overlook what will undoubtedly be the starting point, which is our moon, the closest one to us, the easiest one for doing something that is in no way easy. But you might be wondering, what all could be needed for a moon base? So let us start with that, by going through simply what stages would be needed for our moon. And these stages would probably be similar for moons like Callisto as well. And we may even be able to look at how some of those might apply to Callisto as we go along. So the truth is, at our current technology, I don't think that building a base on any moon is totally feasible. We're still working up to that. And definitely not in one go. In fact, this is what the Artemis program is aiming to do. It is taking us along these steps, or some of the steps needed to get to this. With that in mind, a phased approach is necessary. And we are, to some extent, already in the first phase with our own moon. And this first phase is all about robotic and unmanned setup, right? The idea here is to get the preliminary equipment in place so that the crew arriving for the second phase will already have most or all of what they need to get right to work on a successful mission. And so phase 2 is setting up temporary habitats. Think of this as a trial run of sorts for a long-term mission. These habitats could be inflatable or modular and set up in advance by robots, and even with some of the parts being 3D printed. I would relate this phase to being similar to the ISS, except it is on the moon. with stays perhaps being months or even a year. And by at this point, we would have also mastered flying to, landing on, and taking off from the moon, which is going to be very important for any kind of extended stay there. And then phase 3, kind of like I mentioned earlier, this phase is the goal that missions like Artemis are striving towards, where we have long-term habitats or even full-on bases capable of housing 100+ people. We have mastered the use of on-site materials and have really enabled our ability to expand to other parts of the moon and even other moons or planets in general. And I could even see a scenario, right, where by the time our moon has reached this last phase, we may even be kicking off earlier phases on places like Mars or Callisto. Another thing to consider here, right, is what sort of instruments and equipment might be needed for setting up and establishing a working presence on the moon. Well, that is why I am here. And let's just start with some examples of this, beginning with mapping and site selection instruments, such as laser altimeters, which are designed to provide comprehensive images of any given moon or even planet's topography, and to help map surface features and their height variations. We've got cameras for high-resolution 3D mapping to further study topography and document potential landing hazards. We also have radar, which will help further map the surface along with the subsurface to identify features that may either help or obstruct the mission. And so again, this is all about the initial research to really choose the best possible place to set up the Moonbase. We also have a topic I covered earlier in the video, which is in situ resource utilization. In short, resource prospecting equipment, such as spectrometers of various types. And you know what? While we're here, to give a quick rundown of spectroscopy, matter leaves an imprint or fingerprint of sorts on light when the two interact. This manifests itself through absorption and emission lines. In short, this allows scientists to use light to determine the composition, structure, and physical properties of the matter being studied. For Moonbase missions, the wavelengths of light that we might use to study further are gamma rays, X-rays, and infrared. One example of what this will help us find is the water ice. This is more important on our moon, but that is not all they would be used for. Because water is so important for so many other things, we would need multiple methods of searching for it. Another way of doing this is neutron detectors that could be used to find potential ice deposits through seeking out hydrogen-enriched soil, and could perhaps help to determine the best spots, like I mentioned before, so this would help aid in finding the best spot for an initial base. Once these resources are located, the on-site crew and staff at the base, like people, are still going to need a way of getting at them. And so units for extraction and processing would need to already be on site and available, right? This would be an example of that earlier, that phase 1 I mentioned, where we would need things on site and ready before human presence arrives there. So examples of this might be ESA's prospect drill to retrieve samples, or a specialized piece of equipment called the ROxygen reactor, I'm probably not saying that right, but it's ROxygen, so ROxygen reactor, whatever, which was developed by NASA, and its purpose is for oxygen production. This goes without saying, but it will remain of the utmost importance to continually monitor the environment of the moon that we are on, for both the safety of the base, but also its inhabitants. To achieve this, we will need equipment to do so. And so, while we are here, let's go over that as well, starting with seismographs. These are essential for measuring things like meteoroid impacts, along with their frequency, and moonquakes. Nobody wants to get caught up in a moonquake. We want this data to help assess structural risks to any potential moon bases, and crew may also want to keep watch on the internal temperature and evolution of the moon. And the piece of equipment that would help achieve that would be heat flow probes. And, along with being interesting data in general, these sorts of things may also let them know if any potentially hazardous events are on the horizon. And I'm sure you've heard a lot of this before. It is hard to talk about being in space without mentioning radiation. It is out there. It is present everywhere in space, and it is in every way, shape, and form out to kill us. So we need ways to monitor it, technology to perceive it, and know if we're shielding ourselves properly. Right? So instruments such as the Lyman alpha mappers or cosmic ray detectors help us to monitor the environment for background radiation, for charged particle fluctuation, to determine what might be coming at us. Now, knowing it is one step, but we also need to shield the crew from it in general. Now, water is a great way to shield radiation, but it is both heavy and is already a precious resource, so we just can't rely on it entirely. But what if we could end up underground, or shielded by the ground in some way? And so another effective and probably more accessible solution towards blocking radiation is to just stick 5 or so meters of lunar regolith or soil between us and the radiation source. While I believe this metric is for our moon, I suspect that similar techniques could be used on Callisto, again, because it's not entirely ice, it has rocky sections as well. So I don't think that would be much different. However, that would introduce us to another issue, and granted we're going to face this either way, which is dust. Dust! Dust! Everywhere. It gets in your machines. It gets in your shoes. It gets in your crack. Anyway, we also need to watch out for dust to ensure that it does not damage systems or interfere with workflow. And to assist with this, we will need dust detection instruments used to measure things like mass, electrostatic properties, and velocity for micrometeorite particles or dust from the moon, and etc., things like that, both of which would be found on our moon and on Callisto. These things can interfere with mechanical seals, they can interfere with solar panels, but we also want to keep the dust out of our bases and habitats as well. So this will call for equipment specialized for cleaning and filtering out the dust regularly, and as we mentioned seals earlier, we will need to develop sealing technology that is highly tolerant to dust. And another consideration to make here is thermal control. Now this will vary depending on where we are. On our moon, the daytime can reach over 250 degrees Fahrenheit, that is hot, while the nighttime can reach negative 208 degrees Fahrenheit, that is both cold and a huge temperature swing. So our habitats, or the shielding around them, would need to be able to maintain a regular temperature inside across that range outside. Like with radiation protection, being underground or insulated by soil in some way, by regolith, can assist with this. Now, those ranges were for our moon. Callisto is much farther away from the sun, and so it is pretty much cold all the time, with its average temperatures being around negative 218 degrees Fahrenheit. But if we remember, as mentioned earlier, Callisto has a lot of rocky sections alongside the ice, so we can very likely implement the same strategy we would on our moon. This means that in both cases, and we have hinted at this already, we will need strategic site selection to ensure that we really end up in the best spot possible. And before we go for today, because otherwise this video will be going forever, let us talk a bit about power. Right? No matter the duration of the mission, it will fall apart if we have no way of powering our equipment. And there are in general 3 ways that we can achieve this. The first being solar power, which is great overall and probably the cheapest option, but it struggles with the length of the day-night cycle. On our moon, we would have 15 or so days in the dark, and on Callisto, we would have 8 or so days in the dark. So during that time, high-capacity power cells would be needed to maintain life support in other critical systems. And batteries don't like cold. So it would be, I think, challenging to reliably store power for that period of time. And if they failed, well, that would be very, very bad. I don't think you need to hear that from me. So to supplement this, we turn to nuclear power, which can take 2 forms. One of RTGs, which are radioisotope thermoelectric generators, which through nuclear material decay provide constant low power output fit for, like emergency use. For that time where we have maybe something that's not drawing a lot of power, but it is absolutely critical. And small nuclear fission reactors, such as NASA's Kilopower project. And this third option in general is considered to be or will be the most reliable solution for high power, constant electricity, regardless of if sunlight is available or not. When we consider what is needed for a base on our moon, I think it is fairly safe to say that in the future, we can and will also achieve a base on Callisto. While the environment between the two is different, many of the challenges are the same, and so the things we learn on our moon will very well apply on Callisto as well. And again, because of its distance from Jupiter, we would not be coming up against unmanageable levels of radiation. So what do you think? Are there parts of this video you would like more detail on? Do you believe Callisto is a future candidate for a moon base? Where else in the solar system might we build bases in general? Sound off in the comments below, as I would love to hear your thoughts. If you like what I'm doing, if you enjoyed this video, if you like my beard, please like and subscribe and hit the bell icon. Not only would I appreciate it, but it is very important for small channels like mine. And with that, I would like each and every one of you to step outside tonight and look towards the stars.